be learned and studied in a whole population or whole people in our living country or living province or even the world. So today we will learn some knowledge of the population genetics. As in population, what is a population? In fact, the word is a large population, world population. But we have our population in our country or in our area that or even the province or area that we live in. So population it is a group of individuals that belong to a species. So here you should know that the population is a same species. It is the same species living in the same area and can interbreed with each other. Therefore, it is difficult to explain the genetic composition of the population and its changes with time and space only from the genetic structure of the individual. So, as we learn from our senior school biology, we know that the significant difference between different species is it can't be interbreed with different species. So here we learn the population is a same species and live in the same area and can interbreed with each other. So here we learn the population genetics. Population genetics. So what are population genetics learn about or study on? The population genetics mainly studies the distribution. The distribution of genetic variations in population and the factors affecting the gene frequency and the genotype frequency in generation by generation transmission. To study the distribution and variation of gene frequencies and corresponding phenotypes in population by mathematical means. So, in the public genetics, we should use the mathematical means to learn about the variation and distribution of gene frequency and in the population. So should maybe we will use some formula to calculate this the genotype or gene frequency. And the task of the population genetics, it is also the central task of human genetics or human evolution and post-genomics. First, we will learn the genetic balance of populations. First, we will learn the genetic balance of populations. In the population, we should learn a law named the Hardy-Weinberg equilibrium law. So, does anybody remember the Winburg? He is a genetic biologist, and we have learned about his some study of him. Does anybody remember? Okay. Actually, the Winburg, we learn about it in our single gene disorders. In the autumn recessive disorder, the AR disorder, because we use his formula to correctly calculate the risk of patients in AR disease. So what is Hardy-Weinberg equilibrium law? It means in a large population. Here you should pay attention that it's a large population and with random mating. So it is a large population, has many people for our medical genetics, because we learn the disease of human. So in the large person, the species is human, with very many people rather mating. The dominant traits did not increase with the decrease of the recessive traits, and the proportion of different genotypes remained stable from generation to generation without the influence of external factors, for example, the environmental factors. So, in the Hardy-Weinberg equilibrium law, it has some limited conditions. A large population rather maintain no environmental factors effect. So here we can see the limited conditions for this equilibrium law. The Hardy-Weinberg equilibrium law. One, the group is large, so it's a large population with many people. Two, a second, it is the mating type or the marriage between them is rather mating. Third, is no mutation in this population, and fourth, no natural selection in its population, and the last is no mass migration of individuals. So here, okay. Okay, you can see my screen?
No, 老师。
Okay. Sorry. You see my screen? Hello?
Yes, 老师。
Okay, sorry. So, first we learn the Hardy-Weinberg equilibrium law. In this law, it has some limited conditions. One is the group is large, so it is a large population with many people. Two, the marriage type is red mating. Three, no mutations. Four, no natural selections. And five, no mass migration of the individuals. So, as this law needs these limited conditions, so one of these conditions may influence the balance of this law. So we will learn about this affecting factors later. But you should remember that the Hardy-Weinberg equilibrium law needs these conditions. Before we learn the application of the law, we should learn or review two phrases. One is the allele frequency. It means the frequency of allele distribution in a population. For example, it means the capital A frequency or the lowercase a frequency. It means a frequency of allele gene. Another phrase is the genotype frequency. It means the frequency of distribution of genotypes in a population. For example, the two capital A or the heterozygous capital A and lowercase a, or the homologous lowercase a. It means genotypes frequency in a population. So use the Hardy-Weinberg equilibrium law. We should learn how to calculate the allele frequency and genotype frequency. How we know that the Hardy-Weinberg law is right or is correct? Oh, maybe we should learn how to study what this law comes from. So first, we see the frequency of two alleles in parents and the frequency of offspring genotypes. Here, the sperm and the ovum. So his offspring is capital A, or the heterozygous, capital A and the lowercase a, or the homologous lowercase a. And the frequency for the capital A is P, and the frequency for the lowercase a is Q. So the AA is frequency is P square, and the lowercase a frequency is Q square. And the frequency for heterozygous, the lowercase a and the capital A is PQ. You can show all this in our PPT or in the table on our PPT. So the second generation genotype frequency, we show it in our table. Here you can see the capital A is the p-fourth power. And all these results, as I show it in our table in the PPT, you can see here, because we are if we all read it, it's difficult for me to read it all. So you can see all this frequency for this genotype in our table. So it is the second generation genotype frequency. Then here we get a summary for the genotypic distribution of spring of various assortments. The mating type for capital AA, and the mating type capital A and heterous A, and here. So the frequency for the upstream of the genotype capital homozygous capital A is here. P first power plus 2 P3 power Q and P square and Q square. So the heterozygous capital A and lowercase a here, we can see his frequency of for his brain in the table, and then the homozygous lowercase a here. So the results in the table show the spring for a double capital A is here. P3 P first power plus here plus H. Then the following can be calculated by, then the final result is P square. Because here in the population, the frequency for the capital A is P and for the lowercase a is Q. So because capital A and lowercase a is a Leo's gene, so the P plus Q equals 1. Because the gene in the locus of this locus is capital A or lowercase a, so the P plus Q is 1. So here, then this volume can be read as this. Then the result is P square. Also for the capital A and lowercase a is 2PQ, and the homozygous lowercase a is Q square. So here we can see the second generation of the second generation genotype frequency is P square, 2PQ, and the Q square. Here the first generation is also P square, Q square, and 2PQ. So the frequency of genotypes in the first and the second generation is the same in this population. In fact, the genotype frequency remains constant no matter how many generations pass. You can use this method to calculate the third generation or the first generation, then calculate their genotype frequency. Then finally you will get the same results. The number of individual per genotype increases or decreases with population size, but the relative frequency remains constant, which is the theory behind the Hardy-Weinberg equilibrium law. So here is where the Hardy-Weinberg equilibrium law comes from. If you have any question, maybe you can ask me after class, okay? Or you can use this method to calculate the third generation or the fourth generation. But further, here, for the X linkage is a special case in which the males only have one X chromosome, and the genotype frequency of the male is equal to the allele frequency. So the genotype frequency for males is about Q or P. Just for the capital A, the frequency of capital A, or the frequency of lowercase a. While that for the female, it has two X chromosomes, so it is the same as the autochromosomes. So here you should pay attention that the X-linked disease for the genotype frequency for the males of the X-linked disease is equal to the allele frequency. So here you should pay attention. After learning what is the Hardy-Weinberg equilibrium law, so next we will learn how to use the Hardy-Weinberg equilibrium law. First, we can use this law to determine if a population obeys the Hardy-Weinberg equilibrium law. If then we can use this law. If the population obeys this law, then we can use this law to calculate its frequency, genotype frequency. If this population does not obey the law, so we can't use this law to calculate its frequency. For example, first we can see an example. A pair of alleles, capital A and lowercase a, with three genotypes, AA, here homozygous A, and we can see from our PPT. In a random population of 1,000, the observed genotypes were distributed as follows. The homozygous capital A is 600 people, and the heterozygous genotype is 340 people, and the here is the lowercase a, and the homozygous lowercase a is 60 people. So with the incidence frequency of this disease, we can calculate the expected value of these three genotypes. And In the example, we have the observation value of these three genotypes, and we use the chi-square test. We use the chi-square test. This volume is on our PPT. Use the observation values minus its exception values with a square, then divided by the exception values. Then we can get the chi-square results. In this population, the result is 1.60607. Use the chi-square test. We can see here. So the result is 1.6007. So we can see it is more than 0.005. It's later than the value here of the 0.05. So how can we explain this result here? Use the chi-square test. When the p more than the when the p-value in the chi-square test value in our PPT and in this box, we use here the 0.005 value and the 0.001 value in our box. When the p minus when this the chi-square value minus than but more than 0.05, there was no statistically significant difference between the expected value and the observed value. Then the allele frequency and the genotype frequency distribution were in the line with the Hardy-Weinberg equilibrium. So this population is obeys the Hardy-Weinberg law. But when the p is less than 0.05, the difference between the expected value and the observed value was statistically significant, and the distribution of the allele frequency and the genotype frequency did not conform to Hardy-Weinberg equilibrium. So, in this condition, the population does not obey the law. So, use the chi-square test, we can determine if a population obeys the Hardy-Weinberg equilibrium law. Then we will see the second example. So here we can see the genotype for the B. The expectation value shown in our table and the observation value also shown in our table. Then we calculate the chi-square test so that the result is 50.082. So from the critical values of the chi-square distribution, we can see it is less than the 0.05. So this population divided from the Hardy-Weinberg equilibrium with the degrees of the capital B homozygous and the increase of the heterozygous capital B and the lowercase b. So this population does not obey the law. So we can't use the law to calculate its frequency, genotype, or allele frequency. The second application of the Hardy-Weinberg law is the allele frequency and the heterozygous frequency. First, you should test whether this population obeys the law. Then you can use this to calculate the allele frequency and the heterozygous frequency. For example, the incidence of the cystic fibrosis and autism recessive genetic disease is about 1,000 in white Europeans, and the patients are homozygous. The Q square equals 1/2000. So the Q equals about 0.022. You can see in our PPT. I don't know how to spell the volume. So you can see all this calculator method in our PPT. So the P equals 1 minus Q equals 0.978. The heterozygous means the carrying genes, mutation genes, 2 PQ equals the 0.043. So use this law, we can calculate. We use the P minus Q equals 1, and the P minus plus Q square also equals 1. Then we can use this to calculate the genotype frequency. Then we will learn the factors affecting the population genetic balance. At first, I'll show you that the Hardy-Weinberg law needs some limited conditions. The large population, random mating, no mutations, no natural selections, and no mass migration. So all this is the factors that will affect the balance. First is no random mating. Random mating refers to the selection of a mate regardless of genotype. No random mating can increase the frequency of homozygous couples in 2 ways. For them, first is assortative mating, means they're choosing a mate with certain characteristics, such as height, intelligence, or race. It will increase the frequency of homozygous, especially in the AR disease, the autosomal recessive hereditary. The autosomal recessive hereditary disease. And the second type is consanguineous mating. It means the marriage among relatives related to a common ancestor. It can increase the proportion of homozygotes and decrease the number of heterozygotes. Although it is also does not change the allele frequency. So we should here you should know the non-radial contains the oscillative mating and the consanguineous mating. In the polygenetic disease, we learned that the risk of the polygenetic disease was proportional to relative rank. And also, we learned the coefficient of relationship, the R value, in the single gene disorder. The coefficient of relationship means the probability that two people acquire the same allele for locus from a common ancestor. So in this table, I summarize the R value at different relative levels. For the first degree relatives, it means between the parents and children or between the siblings. The relative coefficient is 1 second. And the secondary degree relatives between a man and his uncle, aunts, grandfathers, and half-brothers, the R value is 1/4. And for the third degree relatives, it means between cousins, the relative coefficient, the coefficient is 1/8. In here, we will learn another coefficient, the inbreeding coefficient, abbreviated as F. It means the probability that inbreeding results in a pair of identical genes in children. For example, the siblings' fathers has alleles A1 and A2 at one locus, while their mother has alleles A3 and A4 at the same locus. A quarter of their children are A1, A3, A1, A4, A2, A3, and A2, A4. If this pair of children are inbred, the total probability of forming A1, A1, A2, A2, A3, A3, and A4, A4 in the offspring is the inbreeding coefficient. We will learn the estimation of inbreeding coefficient. Take a locus on the outer chromosome as an example. Here in our PPT, we can see this picture. It means the gene transmission in sibling mating. The frequency for the S has the A1 gene or the A2 or A3 or A4 frequency. So here, the A1 can be transmitted from P1 to B2 and from P1 to B1. So the frequency is about 1 second. And then also then the S will be the A1. Then the B1 has the 1 second opportunity transmit the A1 to the S, and the B2 also has a 1 second opportunity transmit the A1 to S. So the S is the A1 genotype is 1, 2, 3, 4. Need 4 steps of A1 transmitted with the opportunity of 1 second. So, and as the same, the A2 and A3 or A4 also need 4 steps to transmit this gene to the S. So, the total probability of S forming the homozygous A1, A2, A3, and A4 is 1 second first power. Then with so its probability is 1/4. So here we can see the inbreeding coefficient between the first degree relatives is 1/4. You should learn the inbreeding coefficient is different from the coefficient of relationship. One is R, the other is F. We can see another example. It's a transmission of allele gene in uncle and niece mating. If the S with the A1 or A2 or A3 or A4 it can here. The A1 can transmit from P1 to B1 then to S, or transmit from P1 to B2 to C then to S. So it needs 5 steps, and all these 4 genes also need 5 steps. So the F value is 1/8, and the secondary relatives, the second degree relatives, the F for the secondary degree relatives is 1/8. So finally, we will get the result in this table. I summarize the result in this table. The relative level, the first degree relatives, secondary, third, fourth, fifth, and the R value is 1 second. The F value is 1/4. For the second degree, the R value is 1/4 and the F value is 1/8. For the third degree relatives, the R value is 1/8 and the F value is 1/18. So you should remember this table. The first factor that affecting the population genetic balance is no non-random mating, and the second is selection. The selection reflects the effect of environmental factors on a particular phenotype or genotype, and it can be positive or negative selection. Actually, in the idealized population with Hardy-Weinberg equilibrium has no selection for genotypes, but in practice, there is often a negative selection for specific defect phenotypes due to the reduced fertility. So in genetics, we use the biological fitness to measure the fertility and reflect the distribution of the next generation gene pool. Here, when the fitness, the F value, here is the inbreeding coefficient means the capital F, and the biological fitness as the lowercase f. It means when the F equals 0, it means hereditary death, that is no fertility. And when the F equals 1, the fertility is normal. So the gene frequency or genotype frequency of the population is affected only when selection occurs before the children bearing age. So here you should pay attention. When the selection factor only affects the population genetic balance before the childbearing age. After this age, it has very little effect on the population balance. For example, but how to calculate the lowercase f, the fitness? Here we see an example. According to a Danish survey, 1,008 people with the dwarfs had a total of 27 children, and there are 457 normal siblings. Of this, dwarfs had a total of 582 children, and the relative fertility rate of dwarfs is F equals. Here, the volume is I show the volume in the PPT. Oh, the F equals 1.2. So from this formula, we can summarize that the F value equals the average number of children born to patients divided by the average number of children born by normal siblings. So the F means the average number of children born by patients, and the divided by the average number of children born by normal siblings. The relative fertility rate represents the fitness. The selection coefficient refers to the degree of fitness reduction under the action of selection, represented by S. Lowercase s. The S reflects the degree of unfavorable existence of a certain genotype in the population. So the S equals 1 minus F. The third factor that affects the population balance is the mutation. The Hardy-Weinberg equilibrium is based on the no mutation assumption. If a locus has a high mutation rate, the proportion of mutant genes in the population will increase steadily. The mutation rate refers to the number of mutations in a gene, in a gamete or a haploid cell. So here you should pay attention. The mutation rate refers to the number of mutations in a gene, in a gamete or a haploid cell. So if in people we have alleles, means where is so you should divide it by 2 if to calculate the mutation rate. And the mutation rates in human genes tend to be low under normal environmental conditions. There are 2 methods to estimate the mutation rate at each locus in each generation: the direct method and the indirect method. First, we will see the direct method. Indirect method: if a dominant gene is present in a child that is absent from both parents, then this gene is thought to be due to a new mutation, because both of his parents have no this gene, but the children have this gene. So Here, use this method, we can calculate the mutation rate in a AD disease, the dominant disease. Because in the recessive disease, if his parents have no pathogenic genes, but his children will also have the disease because his parents may be the carriers of the disease. Here, in the direct method, the mutation rate equals the patients in the population minus the patients with genetic disease, then divided by the total number. Here, we should use a 1 second. Why? And because we here in the definition of the mutation rate, it refers to a number of mutations in a gene in a gamete or haploid cell. So here we should multiply 1 second. Here we show the here we show an example. Also, the achondroplasia disease is a dominant hereditary disease, and it is complete dominance. Here, your petition. This disease is completely dominance. One of a total 94,078 delivers. 10 children have this disease, but 2 of the children had a parent with this disease. So they are excluded. The parents of the remaining 8 children were normal and could be considered the result of the new mutation. Then, and the 980,073 children born to normal parents, representing 188,000 and 146 gametes. So we can calculate the mutation rate, the mu, as h divided by the 188,000 and 146. It equals this. Here, we also the results in our PPT. Then, use the direct method. There are many conditions. There are many limited conditions. One is this disease must be autosomal dominant inherited disease. And second, the penetrance must be 1000%. And in this disease, there must be no phenocopy and no heterogeneity. And finally, there can be no early death. So use this method. Very little disease can be calculated by this disease. And here, the penetrance, the phenocopy, and heterogeneity, you can review them in our single gene disorder PPT, because this is all the factors that will influence the risk of the segregation disease when we calculate them. So this method is therefore limited to a few diseases. Then we will see the indirect method. One assumption is that gene knocked out by patients with low fertility are compensated for by new mutations, thus maintaining a relatively stable gene frequency in the population. Because the mutation rates are estimated based on the number of genes eliminated, so they are an indirect method. So the indirect method means that the genes knocked out by the patients with low fertility are compensated by new mutations. Here we use the the biological fitness and the selection value. So you should first calculate the F value. For example, the mutation rate of the achondroplasia dominant gene is measured by indirect method. First, we should calculate the F value. Then the F value is 0.2. Use the patient, the average number or the average children born by the patient and divided by the average children born by the normal people. Then the incidence of the dwarf gene population is better estimated as 10 divided by 94,035 for this gene. So these people had so many genes, while the 10 children had 20 genes, but half of these are this coding gene because in the autosomal dominant gene disease, the heterozygous may have the disease, and the homozygous capital A may be dead before birth. So gene loss to reduce fertility were compensated for by new mutations. Then we can use the mu equals SP, and the S equals 1 minus F. Then we can calculate the mutation rate as the result. So this value of the mutation rate is consistent with that of by the direct method. In the same way, the mutation rate of a recessive gene can be calculated by direct method, but it should be understood that for every recessive individual, there are not only one but two lost alleles. So once you know the fertility and morbidity of the patient, you can calculate the mutation rate. The only difference is that you don't divide it by 2. So here I summarize the mutation rate of Munder genetic disease. The AD disease, mu equals SP, and the AR disease, mu equals SQ square. And the S-linked recessive disease, the mu equals SQ divided by 3. Because here in the X-linked recessive disease, most of the patients are males, and the males only have 1/3 X chromosome. So here the volume is mu equals SQ and divided by 3, and because the male only have one X chromosome, so the frequency is Q, not Q square. Finally, you should remember these three formulas for AD disease, AR disease, and X-linked recessive disease, XR disease. The first factor that will affect the balance is a genetic shift. In large populations and normal fitness conditions, the number of offspring tends to be balanced, so the gene frequency remains stable. But in small or isolated populations, there may be a higher proportion of gene in the offspring, and the gene frequency changes significantly from generation to generation. This phenomenon causes a random genetic drift, also known as a genetic shift. Here, in the genetic shift has a founder effect. So what is a founder effect? It means the initial population that the foster population has a significant effect on their offspring. It means the founder effect. Finally is the migration and gene flow. Migration is the movement and intermarriage of different people. As populations migrate and mix, new alleles enter another population, resulting in a change in gene frequency. This mixing of alleles across races or boundaries is called a gene flow. So all these 5 factors that will influence the population balance is the limited conditions for the Hardy-Weinberg equilibrium law. Finally, we will learn some knowledge of a genetic load. What is a genetic load? It is composed of all harmful genes that lead to the decrease of fitness in the population, mainly including the mutation load and segregation load. They are affected by inbreeding and environmental factors. A mutation load is the main part of the genetic load due to the harmful or lethal mutation of the genes and reduce the fitness, then cause the load to the population. The mutation load depends on the mutation rate mu and the selection coefficient S of mutant gene. Because we saw that mu equals SP or SQ, and the SQ divided 3, so the mutant rate depends on the mu and the selection coefficient. Another is segregation load. Due to the marriage between the heterozygous and heterozygous, 1/4 of the offspring are homozygous lowercase a, then it will reduce the fitness, thus leading to the decrease of the population fitness, resulting in the increase of the genetic load. If the S value of the homozygous is larger, the decrease of the fitness is more obvious, and then the increase of the population genetic load is more significant. And from his definition, we can show the genetic load are affected by inbreeding and environmental factors. So the factors affecting the genetic load is the inbreeding and the environmental. Because the inbreeding will increase the homozygous, especially in the recessive disease, and the environmental will cause the gene mutation. For example, the physical factors and the chemical factors and the biology factors. The environmental influence, we learn this knowledge on our gene and gene mutation class. Then you can review the knowledge on that from that PPT. Finally, I have a summary for our class, today's class. In this class, you should know the Hardy-Weinberg equilibrium law. Then you can know the two applications of the Hardy-Weinberg law. And then you should know the 5 affecting factors: the non-random mating, the selection, mutation, gene shift, and migration, and gene flow. How they can affect the population balance. So this is all the the knowledge for our today's class. So we will start. If you have any do you have any question? Hello.
No, 老师。
Okay. So today's class is over.
No 老师。No 老师。OK 老师，谢谢老师，谢谢老师。
谢谢老师，再见。
Is Li Tong there?
Yes.
Li Tong. Is Li Tong there? Hello.
Yes, 老师。
Is there a monitor? Li Tong. Hello.
Yes, 老师。
Can you hear me?
Yes.
Okay. Today only about 50 students is in our class, so there is about 10 students is not in our class. You should record their name, okay?
OK，老师。
Okay. So today's class is over. Bye bye.
谢谢老师。
嗯